Hello friends, in this third lecture of RCC, we will discuss how to find percentage limit of AST, PT limit or PT max for a balanced section. Before that, I will explain again what is balanced, over-reinforced and under-reinforced section. RCC is like a three-legged race. In the first photograph, you can see the two persons, the two boys, fail simultaneously. We will call one as concrete, other is steel. They both fail simultaneously. In our language, we call this as balanced section. Here, XU, that is depth of neutral axis, is XU max. In the second case, in the second picture, you can find concrete fails first. Steel is stronger. Steel is more than what? More than that required for balanced section. So we call this section as over reinforced section. In this case, XU is greater than XU max. As concrete fell first, it is a brittle material. The failure is sudden. Person do not get any warning of failure. So in that case, casualties are more. So IS code does not allow to design this over reinforced section. Here we get XU is greater than XU max. In the third picture, steel is weaker. Steel fell first. Concrete is intact. Steel is ductile material. Its failure is gradual. One can get warning before failure in the form of well distributed cracks at the surface and large deflection. So, IS code always recommend to design under reinforced section. In this, XU is less than XU max. Now, consider the stress diagram. Here, there is a rectangular singly reinforced section, and this is a stress diagram. As usual, B is the width of the section, capital D is overall depth, small d is effective depth, area of steel, that is steel bars are provided on tension side. The stress diagram for concrete is rectangular plus parabola. The total compressive force Cu given by concrete is 0.36 FCK XU max. Here, as I am considering it is a balanced section. So I will call XU as XU max. So XU max into B is the total compressive force given by concrete. Then TU, that is the total tensile force given by steel, is 0.87 Fy into AST. These two forces are unlike parallel forces, they forms a couple. Now let us consider a beam, a simply supported beam of span say L meter. This is a simply supported beam of span L meter, and it is loaded with a factored load, or you can say design load, or ultimate load, UDL, WU kilonewton per meter. W is what? Ultimate load or factored load or design load. Now in this case, the bending moment diagram is a parabola having maximum bending moment at the center, which is equal to WL square by 8. This is maximum bending moment due to external loading WU. So we can call this as external bending moment. External bending moment. Now, to resist this external bending moment, there must be internal bending moment, which is known as moment of resistance. Moment of resistance. It is called as mu. So mu must be equal to Bm max. So action is bending moment maximum, reaction is mu, that is moment of resistance. This mu is given by a couple produced by Cu and Tu. So Cu and Tu both are equal. They are equal unlike parallel forces, and moment of a couple, in this case mu, is equal to either a force Cu into Z. Z is lever arm, that is the perpendicular distance between the two forces forming a couple, or it is also equal to Tu into Z. Now, as Cu is equal to Tu, I will repeat, Cu is total compressive force given by concrete, that is 0.36 FCK XU max into B. See, I am considering the balance section, so I am writing XU max. Here 0.36 FCK is average stress, average compressive stress in concrete, whereas XU max into B is area of concrete which is under compression, that is area above the neutral axis, XU max into B. So stress into area, we get force. So this is compressive force given by concrete. This must be equal to Tu, that is the tensile force given by steel, which is 0.87 Fy AST. Here again 0.87 Fy is stress in steel and AST is area of steel. Again, stress into area, we get force. So force in concrete is equal to force in steel. Now I will consider the combination of grade of steel Fe250 and grade of concrete M20. For Fe250, we know that XU max is equal to 0.53 D. Now I will substitute all these values in this equation. So 0.36 FCK is 20. Remember, for M20 FCK is 20 and Fy is 250 for Fe 250. So 0.36 FCK XU max is 0.53 D into B is equal to 0.87 Fy is 250 AST. Now 0.36 into 20 into 0.53 divided by 0.87 into 250 is equal to AST upon BD, and for percentage I will multiply both the sides by 100. So if you calculate this, what you will get, AST upon BD into 100 is equal to 1.76. This is percentage of AST, and as this is for balance section, this is PT, percentage of steel maximum, or PT limit. Similarly, you can calculate PT limit for combination Fe 250 M25, Fe 415 M20, Fe 415 M25, Fe 500 M20, Fe 500 M25, because these are most combinations used in various cases. See, for this Fe 415 and M20 combination, Fy is 415, FCK is 20, and XU max is equal to, for Fe 415, we calculated this last time. For Fe 415, XU max is 0.48 D. So here you can substitute the value of XU max 0.48 D for the combination of Fe415 and M20. And after substituting these values in the equation Cu is equal to Tu, you will find the percentage limit for various combinations, and these values are written in this table. So see that while you are designing, the percentage steel is never greater than 0.96 for combination Fe415 and M20. Otherwise, it will be an over-reinforced section which is not allowed by IS 456 2000. So this complete our today's lecture number 3. Thank you.